or?
So, okay, I'm just starting the recording here so that we can capture the questions on here. The question was, what's the difference between SAS proc univariate and SAS proc means, generally?
Mm-hmm. Mm-hmm.
They have a lot of overlap. Proc univariate has more options for what it provides. So proc means gives you descriptive statistics for quantitative variables that are more limited in scope than what is possible using univariate. Univariate also has a function to do histograms and to have curves overlay the histograms. So with respect to finding like the mean and the variance and stuff like that, you can get that out of either.
Mm-hmm. So you mean proc univariate has more information rather than the proc means, right?
That is correct.
Mm-hmm. Thank
Yes,
you.
there are more output possibilities, I should say.
Mm-hmm.
More things are spit to the window by default. We had
Thank you.
another question in the chat window. Take a number I already have and do the math with it. How do I do that in R? You can actually type that in the console window or in your R program. Just do the math and it will work like a calculator.
Okay. Even if it's, so like I was given the frequency of the non-binary variable, and I just wanted to take 1 minus that to get the frequency of the other two added together. So do I plug in just the numbers that it gave me, or how do I plug in that variable so that I didn't round it? Does that make sense?
Yes.
Or do you care?
It only needs to be correct at 2 decimal places. So I'm guessing if
then
it spit
it
out
doesn't
enough,
matter.
that should work. In general, there are ways to access where the number is stored so that you wouldn't have to type the number, you just refer to where it is, but that takes an additional level of coding that I haven't demonstrated yet. I can send you an example of what that would look like if you want to know.
I took care of it. It's fine.
Okay, but yeah, you can use it like a calculator. And Stata works like a calculator too. If you just type display and then what you want it to do for math, it will print the result of the number. So hello everybody who's just joining us. We're talking homework questions. Your first real homework is available right now and due next Monday. The most difficult part will be getting this software to either download on your computer or figure out where your data set is. Honestly, once you get those things resolved, you are home free. And that is actually the purpose of the homework, is just to break us in on these new systems of how to do things before we get to material that should be unfamiliar. So just descriptive statistics once you tackle the hurdle of getting the programs working properly. So any other questions on that while we're on the topic?
I just had a question. When I use the file location, like previously we used example 1, now I use the homework 01. It works when I try to calculate the mean, but doesn't work when I try to calculate the frequency and proportion.
Okay, which package are you using?
R.
In R. I would double check that the variables you're referring to are inside the homework 1 dataset. So you might have the wrong name for the variable that you're asking the frequency for. And if it looks like it's the right name, check the capitalization. Because like Mary with a capital M is not the same as Mary with a lowercase m. Yeah, that idea is case sensitive, by the way, which R and Stata both are, and SAS is not.
And it shows that homework 01 not found. File not found, basically.
File not found. Okay, then it may not have found the original Excel file that you're importing to become homework 1. Have you set the working directory from inside R yet?
Yeah, because it's working for mean, but not for proportion and frequency.
Okay, so you have the data imported, it's just not working for that particular command. Okay, I would say double check the placement of your parentheses and commas. And if you can't get it figured out, send me a screenshot of what you have and what the error says, and I'll see if I can troubleshoot.
Thank you.
Sure. Okay, other questions? No, we're good? Good enough anyway, good here. Thank you for being here, everyone. So heading back into then what we were talking about in terms of new stuff. getting started in general linear models, and in particular general linear models with a single predictor this week, heading into multiple predictors eventually. What did we talk about last time? What do you remember? I'll take words, letters, gestures, pictures, centering. What's centering? We did talk about that.
It's a meaningful place to know where you're starting.
Yeah, it's redefining your predictor so that 0 is meaningful. So you can think of your model as being centered with respect to what the intercept represents, like the "you are here" sign in an airport map. The intercept is going to be the expected outcome when all your predictors are 0. So we center predictors, we rescale them by subtracting a constant so that 0 is a meaningful place with respect to what the predictor variable values could possibly be. So as an example, I'm looking at a predictor of years of education. There was no one in the sample with 0 years of education. Even though it's theoretically possible, it's not very useful. So I centered education by subtracting 12 to create a new column that then becomes the predictor variable in my analysis. That way the intercept refers to somebody with a high school degree as my "you are here" sign. And then we can talk about what happens as you increase in education beyond that or decrease below that. So yes, that's one thing we talked about. What about, what's the standard deviation tell us? Vocabulary drill.
How far on average an individual person is from the mean?
Yeah, so standard deviation is a sample descriptor for the spread around the mean of a variable. How far on average any one observation within your sample is from the mean. Yep. How is that different from standard error?
Standard error has to do with not the person, but like the data, how likely that the mean is close to like the true mean or something of the sort.
So it's not about the people, it's about the samples. So a standard error refers to a distance of a sample summary statistic relative to what that same statistic would be in the population. So the true mean, for instance, which we usually don't know, but we have a way to approximate how far off we are using the formula for standard error. And how consistent, yeah. So if you think about the direction of what more means, a greater standard error corresponds to more inconsistency, more deviation, more wiggliness around what the true answer would be across repeated samples of the same kind. So standard error is a function of standard deviation. The more spread out the people are around a mean, the higher the standard error. Standard error is also a function of sample size. The more people you have, the more consistent the answer will be across repeated samples. The less far off you will be from the right answer. Good. What else did we talk about? Anything else that I'm forgetting? Big stuff? All right, well, let me get the screen share going then, and we'll jump back into where we left off. We're looking at pictures. Move this thingy out of the way. There we go. So I'm picking up on slide 25. So this demonstrates why we would go to the trouble to center our predictors by subtracting a constant. It's so that we're changing where the intercept is, where the 0 point is with respect to the X predictor. So if I left it uncentered in this example, people who have 0 years of education would have an expected income level of negative $7,000. That's not very useful. So we change it so that our reference point is the middle of the picture here with respect to education at 12. Now beta 0 represents the average income level as predicted by the model for somebody with 12 years of education. And beta 1, what's that thing called? Looking for a 5-letter word starts with S. I think it's 5 letters. Yeah, it's definitely not a 4-letter word, although you might be thinking that.
Is the slope?
Slope, yes, indeed. So rise over run, change in y, perch, unit change in x, however you want to think about it, it's a slope. So all slopes are defined the same way. The only difference is what are the variables that they're referring to. So in this case, the slope estimate for beta 1 given these data is 1.82. That means that the model says for every additional year of education, the income level of a respondent is predicted to be higher by 1.82. So that's in thousands of dollars, so about $1,820. That is a prediction given by this line specifically, because that is what our model says. Now, that may not be a reasonable model. And in fact, I'm going to trick out this model in subsequent examples to get something that looks a little more realistic, because we all know that one more year of education doesn't get you the same bang for your buck as at different points on this axis. So if you're talking about the difference between being a high school dropout and having a high school degree, that's a bigger difference than, say, going from 12 years of education to 13 years of education. So later on, we'll tackle that aspect of the data, but for now, we've just got a slope that's going through here. And so I want to make a point about how the slope is the same number in the equation on the right as it is on the equation on the left. So by centering education, we have not changed its slope. It is the same, and it will always be the same in a model in which that variable doesn't have any other relationships with other variables, interaction terms. What changes is the intercept. So that means, practically speaking for you, when you start to do homework using these types of models, one of the first things that I'm going to ask you is, what is the fixed intercept? If you don't get that right, it is probably because you don't have X centered correctly. If I ask you to center a predictor at 5 and you forget and you put in the original predictor, you'll get the right slope, but you won't get the right intercept. So it's the intercept that is a function of centering at this point. And we can choose whatever value we want to center it around. There's no wrong choices, just some weird ones. So we want to try and stay away from those. All right, so moving on then. So more generally, these betas are referring to what's known as fixed effects. So you can have fixed effects that are intercepts or fixed effects that are slopes. An intercept is always the expected outcome when your predictors are 0. A slope is always the change in y for a 1-unit change in x. And in formulas that follow, I will use this lowercase k to represent the number of fixed effects in a given model. It's always going to be the number of betas up here in this equation. So right now there's 2 fixed effects. Another new term. Did we talk about this last time? I don't know if we did or not. I don't think so. Okay, so this is new. See, I warned you that statistics is not about math. It's about vocabulary and language and working memory and putting it all together. So here's a new vocabulary term. The idea of what does the model say your outcome should be as a function of the predictor variables that are included and their fixed effects. That prediction that's given to us by this part right here gets abbreviated into something called y hat. So the little caret thingy over this is known as a hat. It's a pointy hat. It's not a very nice hat, but that's what people call it. And the little I on here is used to indicate that each individual in your data set is going to have a different predicted y hat as a function of their predictor variables. So what the model says y should be is y hat. Another way of writing it is, if y hat is just this part, then the original y is broken into what the model says, that's the y hat part that's in red, plus how wrong is the model. So E is error or residual. Those terms are interchangeable, but I prefer the term residual. And each person has one. E picks up the difference between whatever the model says and what the actual outcome should be. So if the model predicts too low, your E is going to be positive because you're actually up here. If the model predicts too high, then your E is going to be negative because you're actually down here. So this term has a lot of synonyms to it. You can think of it as the predicted outcome, the expected outcome. Another term that you will see is conditional mean, because if we didn't have any predictors in the model, y hat would just be the mean. And now that we have added a predictor x, y hat is conditional on x. So it's the mean for people with this value of x. Like everybody who has 12 years of education has the same y hat. So it's still kind of like a mean in that it's a summary for people of the same kind. It's just that it's conditional on what the predictor value is that is creating the kinds, so to speak. So a lot of synonyms for this. The most important part of trying to decide how good of a job we've done with this slope predictor is talking about what happens to the collection of e's across people before we include it versus after. So we still are interested in summarizing how variable these E residuals are for our sample, and we want to compare how variable they were to start with, like what was the variance of the outcome to begin with from the empty model versus what is it now after we've controlled for a predictor. And so this term right here, sigma squared sub E, what that means is the variance of the E residuals. That term is going to be called residual variance. So variance of the E residuals. And it is computed almost exactly like it was before with two minor switches. So rather than having variance be y minus y bar, individual y minus the mean, now it's y minus y hat. So the conditional mean. So inside the parentheses here, the thing that's getting squared is just E. So you'll see it written in each of these different ways, which is why I'm trying to show the equivalence here. So how far off from the predicted y hat outcome are you? Okay, that's your E. Square that, add it up across people, and now we're going to divide by n minus 2 instead of n minus 1. And the reason that it's n minus 2 is because in order to figure out what each person's E actually is, we had to already know two things. We had to know what beta 0 is, and we had to know what beta 1 is. So this idea of, okay, how many things did we have to know to be able to do this is going to be called denominator degrees of freedom later on. If you've heard that term before, then that's what I'm talking about. And the key idea is that if X is useful, then the variability of these E residuals should be lower after including it in the model than before. Okay, how are we doing? Down? Did I see a thumbs down? Are you just messing with me?
I'll get it. I just need practice.
Just need practice. That's fair. New information is not going to sink in right away. It takes sort of an absorption level. But I got pictures. Do we like pictures better than symbols? Okay, this is a very dense slide, but hopefully it will help sort of make these things a little bit more concrete. Okay, so we're going to predict this person right here. This person makes $58,000 a year, and they have a centered education value of 8 as their predictor, which means that they went to 20th grade because 0 is 12. So we're going to predict this person's income. So if I start with an empty model, remember the term empty model means no predictors. It's the simplest model, it's the worst model, it's a starting point. So for each person, the model is the same. For this person, I am saying that beta 0, if I know nothing else, my best guess for what any person would get is the mean. So that's given by this flat purple line in the picture here. That's the mean of this outcome. If I just ran descriptive statistics, I'd get 17.3 back. So this is kind of a bad guess for this person. They are off. Their E is residual is positive 41.5 because that is the difference between what the purple line says they should be and where they actually are up here. So 41.5 is like all the reasons why this person makes more money than everyone else. We don't know what they are, but it's that much. So if I figure out what E is for each person, and I take that E, so y minus what the model says, E is the interior of this parenthesis here, square it, sum it, divide by n minus 1, then the answer is 190. That is the variance of income in this sample. And if I took the square root of that variance, what do I get? More vocabulary drill. If I took a square root of that variance, what do I get?
Standard deviation.
Ding, standard deviation. So it's like 13.8 or something. We looked at that before. So on average, people are off from the mean by 13.8. That's what this model says. So it's just a recreation of the mean and variance of the sample for this outcome. So now this person, if we add my centered education, here's what the model says. So I'm rounding the numbers to make it a little easier. So the prediction for this person now starts off with my beta 0. That's my fixed intercept. So 14 is what the model says income should be for somebody with an education of 12 years. When this term drops out, it simplifies down to 14. But this person has 8 more years of education than the 12 that is our you are here sign. They went to 20th grade. So if I work that out, their predicted outcome variable for annual income is 28.4. So that's their y hat for this focused person is 28.4. Now that's closer to what they actually got, but we're not there yet. This person still makes more money by $30,000 than what this model predicts. So where this 28.4 is located is right here on this regression line. So the red part, the distance of the E between the empty model flat line with no predictors and after adding education, that distance we would say has been explained by the model. Part of the reason why this person makes more money than everybody else is because they went to 20th grade. But that's not it. We still have all of this remaining deviation for this person to think about. Why else does this person make so much money? I don't know yet. The question we have to answer, though, is across the sample, did adding this predictor actually help? How much of this E distance has been accounted for by where the line is and how much is remaining? So if I do the same formula, I figure out what the line predicts y is supposed to be for each person. That's my y hat. I figure out what the E leftover residual part is. That's how far wrong the line is for that person. That's the idea of error, residual, leftover, discrepancy, all those words put together. Now I find that if I take all of the E's and calculate their variance, it's down to 162. So it used to be 190, now it's 162. So what we're eventually going to do is figure out by what proportion the variance was reduced by putting in predictors, and that's going to be something called our model R-square. That's coming down the road, but for those of you who've heard that term. But this is a way to quantify how good of a job education did in predicting this outcome. Okay. Questions. Is unexplained part counted as E? Yes. So between these two models, the definition of what E is has changed. In the purple, empty model, E is all the distance from the purple line to each of these points. After we add a predictor, then we switch to the blue line that's not flat, that's driven by education, and now E is just the distance between the point and where the line says they should be. So part of the distance is explained by adding that line, and the other part is still out there. Can you tell me where we got the numbers 14 and 1.8? Yes, that's what SAS said. So in the data set, I made it do the math. There are formulas by which I could show you where the numbers come from. I don't know that that's terribly helpful until you understand sort of the concept of what these numbers represent. What I can tell you is that how SAS figured these out is by determining what combination of these numbers would result in the smallest possible collection of E's for that model. The answers that pop out are the ones that make the set of E residuals the smallest collectively. Another way of saying that is that they minimize the sum of squared residuals. They minimize this function. And so these are the numbers that did that best given this sample of data. If I had another sample of data, if I did the exact same study over again, I'm not going to get these exact numbers back. But that actually then segues into this. So one thing that's not on this slide yet is how good are these numbers? 1.8 is the slope this time. If I redid this study with another 734 people, am I going to get a slope of 1.8 back again exactly? Nope. I might want to know, okay, how wiggly would that be? How inconsistent would that be across repeated samples? Like, is it the slope is 1.8 or is it like, I don't know, 1.8 or something? Can you think of a term that goes along with that sort of idea? Of how inconsistent that slope might be?
I just said consistent, sorry.
Yeah, that works too. But like a statsy term, like maybe one of our vocabulary. Margin of error, yep, very close.
Standard error?
Ding, that's it. Standard error. Yeah, slopes have standard errors too. And so do intercepts. So that's another piece of the puzzle. In addition to what is the best answer that collectively makes the E deviations the smallest, we want to know how good that answer is. And that's not on the slide yet, but it's coming very soon. Let me see what's next. Oh yeah, that is next. It's like I made this lecture. It's like, I know I have that in here somewhere. Is that next? It seems like it should be next. Clearly, I am internally consistent in what I think the order of these things should be. All right, questions? Okay-ish? Thumb sideways or higher? Getting there? Okay, that's all. That thumb sideways is a good goal for right now. So the same idea of inconsistency. How much are these results expected to vary across samples? And we can use that estimate of inconsistency to test hypotheses, to answer questions about whether or not these results are noteworthy or whether they're sort of I'm stuttering now. They are reflecting expected fluctuation. That's where I was going with that. So let me show you how this works. Fake people to the rescue. And I have the same typo. I have spelled this number wrong like 3 times across my sides. It's like I just got in a groove where this is 100,000, give or take. Or maybe I meant to demonstrate inconsistency in an estimate. Maybe this was like an error I did on purpose. I'm not that smart. No, I just screwed this up again. I will fix it some more. So 100,000 fake people. I made up a predictor that has a mean of 0 and a variance of 1. And I made this model, and here are the answers that I put in this fake data set. So I set the fixed intercept to be 100, and I set the slope of x to be 2. And then I varied whether or not the variance of the e's that is left would be 9 or 25. So basically, this model would be wrong for a person, would create an E error discrepancy that is about 3 on average, square root of 9, or about 5 on average. So those are the 2 things that I varied. The rest of this, because I made the data, I made it the way it is. So let's see what happens to my slope estimate that's supposed to be 2 if I take 100 samples of different sample sizes and with different residual variances. So this is another demonstration here. So these pictures are like what we were looking at before. These are not people. They're samples. Quick question, does having more predictors reduce E? Yes, if they're good. But if they're not good predictors, then no. So that's one of the questions we have to answer about each predictor to be added is like, does it really help? And does it still help if we already have other predictors in the model that are related to it? So yeah, good question. So inconsistency of the slope, that's what we're looking at here. So if I have repeated samples of 10 people from my fake data set, I calculate what the intercept and slope are supposed to be in that sample. This is a distribution of what the slope ended up being across 100 repeated samples of 5 people. The right answer is 2. That's this line. I drew another line here where 0 is to make a point that if you only have 5 people, the answer that you get for a slope, which is supposed to be a positive number, it could actually be negative. So sometimes just because of the set of 5 people that I picked out, the slope is so wrong that it's in the other direction. So it's really inconsistent. And if I have 10 people and the model does a less good job, so the E variance is relatively bigger, then the results are even noisier. I could get a slope anywhere from 7 all the way down to like -4. Really inconsistent across samples. So as we get more people, we get more consistency. So pretty much all of the time, if I have 50 people, I got a slope that at least was a positive number. And it's noisier if I had more error left over. So it turns out the same factors that affect the standard error of a mean affect the standard error of a slope in the same way. If I got more people, then any one sample slope is going to be more consistent with what it's supposed to be. You'll see less variability across samples in what the slope ends up being. And if I have a better model in terms of the variability that's left over, if the E variance remaining is smaller, then the slope is going to be better too, more consistent. So I have what the actual spread across samples is of the slopes in my fake data here as the standard deviation column, and then what the standard error of the slope is calculated to be given the formula I'm about to show you, and it gets to be pretty close. So with more people, it gets more and more close. But it's the same idea. More people, more consistency across samples. More variance within a sample, less consistency. So then back to this example, these are the values in our data that resulted in the smallest collective set of E's for this model. So our best guess as to what beta 0 should be in this sample is 14. Our best guess to what the slope of education, beta 1, should be is 1.8. And the variance that's left is this 162. So I can use those values to compute what SAS, Stata, or R is going to tell me the standard error is for this slope. The formula is the residual variance of Y, so the variability of the E's that are left across people, divided by the variance of the X that the slope is for, because you have to take into account scale, right? Like 1.8 as a slope only has meaning in the context of years of education and $1,000 of outcome. So we got to know the variance of X in the same way that we got to know the variance of Y. And then it also wants to know our sample size minus the number of fixed effects. So if I plug in the values for this data set, I end up with the slope standard error of 0.16. So that tells me that for this sample, the slope was estimated at 1.82. But on average, any one sample's slope is expected to be off from the true answer by plus or minus 0.16. So that's my margin of error, so to speak. That's how wiggly or inconsistent that answer is expected to be. Now that's pretty small, and it's small because we got a lot of people. So even though we don't know what the correct answer is supposed to be, and even though we don't have repeated samples in real life, we can still use this machinery to anticipate how inconsistent our results would be across repeated samples. I hear an unmute. Is that a question or an accident?
have a question.
Hit me.
Hey, Lisa. So what does the standard error of the slope mean for the direction of the slope? Does that impact it in any way?
Nope. Nope. You would not interpret it any differently if the slope were positive or if the slope were negative. Other questions? Question in the chat. How does the number of people in sample size change the comparison of mean of samples? For example, if there are 10 people per sample and we have 10 samples versus 100 people per sample and 10 samples. Oh, so the sample size only matters with respect to how many people are in a sample. I picked 1,000 samples a couple slides ago. I only picked 100 this time because it was running slower on my computer that day. The number of samples that I'm using to demonstrate this really has no bearing. It is the sample size within a sample that matters. More people within a sample means the results are going to be more consistent across however many repeated samples you have. All right, then the last one, standard error of the intercept. Kind of like standard error of the mean, but with an additional complication. The standard error for an intercept, what you're actually talking about is what is the expected margin of error around any predicted outcome. Because the intercept is the predicted outcome specifically when x is 0. And you could figure out what the predicted outcome is for any x. And you can figure out what the expected inconsistency via the standard error is for any x as well. So the formula starts off with the ingredients that we had before, the amount of variability in the residuals, so how spread out people still are, even though you gave them a regression line, sample size, and then this part in here is a reflection that predicted outcomes at the mean of the predictor are going to be the most precise, and the further you move away from the mean of the predictor, the noisier a predicted outcome is going to be. And I think I have in my work bag next to me here, oh good, it's a demonstration. This thing. I have a collapsible pointer stick that I have carried in my work bag for like a decade and a half. Because when I very first started teaching as a postdoc, people thought I was a college student a lot of the time. And this made me feel professorial. I don't have that problem anymore, but I still like to carry the stick around just because. It comes in handy when I'm teaching in person and people fall asleep, because then I can like poke them from a distance, and still maintain 6 feet of space. But the reason I got this out of my bag here is to make a point. If I got a flat line here, right? My empty model is a flat line. Now let's say that I make it a positive slope. See, is this positive from your direction? It's this way, right? Or was this way? Yeah. Nope, this way. Okay, yeah. I have a severe spatial reasoning deficit, like severe, like I get lost in a closet level of severe, and I cannot do the mental rotation to make sure that it's right in my head. So you got to tell me, this is a positive slope?
No, that's a negative.
Damn it. Okay, this way. All right. So this is now my positive slope. Now watch what happens to where my fingers are as I move the slope. They don't really move very much. But if I put my finger at the end of the stick and I move the slope, it moves a lot. I think this is called a fulcrum in like physics and stuff. Is that a word? Am I using that correctly? Yeah, like a point of like where it bends. And the same is true here. Like if I have a regression line that's flat, then basically everybody has the same range on here. But if I tilt it, then there's a bigger impact of the slope at the ends. So there's less certainty about where you're supposed to be as a function of the slope the further out you move. And I have a picture of that. Not this slide, but soon, I think. I have a picture of it. Oh, I had a picture of it. It's in here somewhere, I swear. I think it's down there. But in this sample, we have a picture of the prediction, and there's a shaded area that basically expands as you get further away from the mean on the slope. So, Computer technical difficulties for some folks, no worries. I understand how that goes. So yes, every result from a model has a standard error. We started with just having a mean as our parameter, get a standard error of the mean. Once we add a slope, we get a standard error of a slope, we get a standard error of the intercept, which is the predicted outcome conditional on x. Yes, indeed. Okay. Other questions? All right, changing gears on this then. That's where I was going next. So standard errors are for everything. They index the expected deviation of that result relative to the right answer, how far off it's expected to be in any one sample. And this idea that a standard error is how far off the sample whatever is from the population whatever, that's going to be like 17 homework questions this semester. I'm just going to put that out there. So I'll do the cough, cough homework question to clue you into that I'm going to ask this over and over again. And the right answer is always, well, what is it the standard error for? Well, then that's the thing it's off from. If it's the standard error of an intercept that you're interpreting, then it's how far off this predicted outcome is from the true outcome. If it's the standard error of the slope, then the right answer is how far off is the sample slope from the true population slope. So the definition never changes. One thing that's potentially confusing is that standard error squared is not a thing we typically talk about. By the way, you might see that referred to as a sampling variance, even though there is a squared analog of standard deviation. So this can be confusing in terms of terminology. Standard deviation is about the people. You square that, you get variance. Standard error is about the samples. You can square that, but we usually don't bother. So moving forward then, what do we do with the standard error? Like, what good does it tell us to know what a standard error is? Well, we can use it to do a hypothesis test. So we want to answer the question, for instance, does education actually predict income? Is it useful? How useful is it? That's where we're heading, is to be able to answer those kinds of questions. So given that we're doing this sort of thought experiment of, okay, in this sample, this is what I got, but I know that if I redid this study over and over again, I wouldn't get the exact same thing. I would get a little bit of variability. The question is, how much fluctuation is too much? And how do we operationally define where too much starts, or where too different from what is expected starts? So what I'm going to talk about here is something that you probably have seen before, but if you haven't, then welcome. This is referred to as null hypothesis significance testing. And it is still the dominating way that people answer research questions in quantitative methods. It requires us to make several decisions ahead of time with respect to, okay, so what do we think should have happened? And then how are we going to define what kind of result is too far away from that, such that we're probably wrong about what we thought should have happened? Okay, so then we have a null hypothesis formally is written as HO, and it's a statement about what is expected. In the context of an expectation for a slope, the null hypothesis that people are almost always going to test is that it's 0. In other words, a flat slope is a useless predictor. Does this slope matter? If the slope is flat, the answer is no. So some sort of deviation, either positive or negative, then indicates that the slope is a useful mechanism for reducing the amount of variability in the outcome. It doesn't have to be 0, but it almost always is. As another example of a different non-zero null hypothesis, you might have a hypothesis about what a population mean is supposed to be, and you can test whether your sample mean is different from that. So that's another type of test in which you would specify a null. But for present purposes, we're just going to say that the expectation that we're trying to test against is that the slope doesn't matter. We want to know if it matters or not, basically. So that requires us to specify the alternative. Well, if it's not 0, then what are we going to allow it to possibly be? And this has to do with whether or not we want to conduct what's known as a one-tailed test or a two-tailed test. And I'll show you why the tail word shows up in there in just a second. But basically, it's whether or not you want to allow the possibility that you are wrong in both directions or in only one direction. So if I say, okay, I'm going to test the slope being 0, if I get a positive slope, am I going to allow that to be different than 0? And am I going to allow a negative slope to be different than 0, or am I only going to let it be one way? And I will tell you that in this class, my personal philosophy is that one-tailed tests are bullshit voodoo, and we're not going to do them. They're cheating. And that is a strong position, but I'm going to say it. Because in most circumstances, a negative slope is a meaningful thing and a positive slope is a meaningful thing. And I am unwilling to cut off either of those possibilities to start with. I might hope that it's one or the other, but because both of them are meaningful, I would want to know about it. So a two-tailed test is written formally like this. Beta 1 is not equal to 0. And if you're looking at stata output, by the way, you will see this. Not equal to 0 with the not being an exclamation point. So both of those means not 0, but it's agnostic as to high or low. Given the result for our slope, and given its standard error indexing its expected inconsistency, we can take those two numbers and form what is known as a test statistic. That tells us, in a standardized fashion, how far away from the null hypothesis our result is. So if we thought something was 0, how not 0 is it? If I take the slope that we came up with, so the 1.82, and I subtract what we thought it was according to the null hypothesis, which is 0, and divide by the slope's standard error, then putting those numbers in from our example, I end up with something that is 11.28. So you might be thinking, okay, what the hell does that mean? I'm glad you asked. So repeating the math at the top of the slide here. So what is this number telling us? In a nutshell, it is telling us that our slope of 1.82 is 11.28 standard deviations away from the null with respect to the slope's sampling distribution. That's kind of a mouthful. But we're using the standard error to describe what is the expected deviation of the slope. So the standard error in this case is very small. It's only 0.16. So we expect the slope to be off by only 0.16 on average. And this is 11 standard errors away from 0. 11 is a lot. So we want to know how often would we find a slope as far away from the null hypothesis that we just found if the null were true. And that leads us to something called a p-value. In order to get that, though, we have to use probability density functions. And these are shapes that tell us the expected behavior of a phenomenon. So we have two choices. They are going to be either a T or a Z, and I'm guessing you have seen these pictures before, like this one. If you've taken intro stat, I guarantee you have seen a picture like this before. Looking at a few of I have a semi-random sample of faces here. The faces are not pleased to have seen this picture again. Like, oh, I hated this thing. And I'm guessing that you had a stats textbook with tables in the back and you had to go to the table and figure out what Z is for a certain level or whatever. Guess what? That's what SAS, stata, and R are going to do for us. So we're not going to have any tables in the back of the textbook anymore. That's not how we do things anymore. But what this thing is called the standard normal distribution. This is a way of predicting how variable a slope result could be across repeated samples. Where in this case, we have boundaries that determine where various percentages of the results are expected to fall. So for instance, within plus or minus 1 standard deviation is about 68% of the data, 96% falls within 2, and almost 99 and some change within 3. So these boundaries here, these are boundaries that tell us how often would you see a result that far away from what you're expected. And if our test statistic is outside of these boundaries, we would decide, okay, that's way too far away. It's unlikely that the right answer is 0. In this context, these are not people. These are samples. So what we are doing is trying to locate where our set of results is in sort of a hypothetical set of other samples just like it. If the right answer is the middle, and if we have a standard error that tells us how far off from the right answer our slope is on average, then we can figure out how often we would find a result that different than 0. This is a way to standardize what we found in terms that are readily identifiable in terms of how often it should happen. This is one way. This is our friend Z. Here's the formula that made this picture, by the way. You don't need to know that. So how unexpected then? That's what we're going to be talking about. How do we determine that? Question. Did I just mention something being 17 standard deviations away from the mean in the previous slide or something? I did. Thank you for the throwback. It was 11, actually. We go back to where that was. This number. So our slope estimate of 1.82 for this data set, we're just working with one answer right now, minus what it was expected to be, which is 0, is the null hypothesis, divided by the standard error for the slope, which is how far off on average any one sample slope is from a population slope. We feed that into this formula. This formula provides us with something called a test statistic. The result of this formula for this data set gives us a value of 11 and some change. What that 11 means is that our slope of 1.82 is 11 standard deviations away from 0, where a standard deviation is indexed by the size of the standard error.
So I'm connecting that with the picture on the next page where like one standard deviation is 66% and 3 is 99.
Yeah, we're
separate things
here.
It's possible to be that many standard deviations away.
Yep.
Okay.
And so it would happen less than 1% of the time that if the right answer for this population were really 0, that any one result would be that far away. We can be. That's what the 11 is telling us here. It is really unlikely that this sample came from a population where the true answer for the education slope is 0. If the true answer for the education slope were 0, we would see our slope of 1.82 less than 1.00001% of the time. Clear the hell out here. Way super unlikely.
I might be jumping ahead here, Lisa, but I'm just trying to connect the dots.
Yes.
So because we have an 11 standard deviation here that's way the heck out there, then that means that 0 is wrong. So we're rejecting the null hypothesis. Is that where we're going?
That's where we're going.
Okay, thank you.
That's where we're going. You can help me get there faster if it's helpful.
No, I'm sorry. I just wanted to make sure I was following.
That's where we're going. Yeah, so basically if it's sufficiently unlikely that we could have gotten our result from this distribution, then we say, yeah, I don't think the null holds. I think we reject the null. And the way that you would talk about that in real life is not we reject the null or we do not reject the null. It's the slope is significant. So yeah, that's where I'm heading, like 60 slides from now, is I'm going to get to the slope is significantly different than 0, p less than 0.05. That's where I'm headed. It's just like all of the underlying steps to get there I don't want to assume that you've seen them, and so I didn't want to take that shortcut, but that is where we're going. Okay. So how unexpected? Where are we going to define the boundaries of where, yeah, that's too far, right? So here are some possible boundaries. If we use the green lines would say that anything past here or here is going to happen 10% of the time or less. If I use the blue lines, anything past here or here on the other side, this is where the idea of a tail comes from in a one-tail or a two-tail test. It's talking about the ends of these distributions as tails. Anything past the blue lines is going to happen less than 5% of the time, and anything less than the purple lines is going to happen less than 1% of the time. So we have to choose ahead of time, like where we're going to draw the line in the sand as to how far away is something before we say, yeah, I don't think this is right. I don't think the null is right because we're too far away. It's unlikely that our sample came from a distribution where the null is true. So how often is unexpected? That's the first thing we have to decide, and that is known as alpha level. It is a probability of finding a result as extreme or more extreme. Like, where do you want to say that's too far? And the most common answer to that in the social sciences is that alpha is 0.05, meaning that we say something is too far away from the null to be believable, that the null is true, if it happens less than 5% of the time. If we want to set an easier standard, so let's say that we have a very small sample size and we don't want to miss anything, right? We want to make sure that we have a very easy standard for what would be a useful slope. We might decide to make the alpha level 0.10. So if I go back to the other slide, now I've moved the bar to this green one here. So it's easier to say that I am outside of expected because more of the area is in unexpected territory. If I want to be conservative, I might pick an alpha of 0.01. So that would be like if I really absolutely don't want to say that something matters when it doesn't. I want to be very hesitant to say that I have an effect. Then I might choose 1% of the time as where I draw the line in the sand for where unexpected starts. So then the tails issue has to do with how you allocate that area. You can allocate the area equally to both sides. That's a two-tailed test. Or you can pool it all on one side and ignore the other side. Sorry. And so these definitions then set up where those goalposts are on your distribution as to where unexpected starts. And, oh, I guess it didn't take 36 slides. It only took a couple. So, so I will say this over and over again because it takes a while to sink in. But the logic goes like this. If your test statistic is inside the boundaries, so you are not that far away from the null, you're within expected sampling fluctuation as given by the standard error. So you're only maybe one standard error away from the null or something like that. Then you would say, yeah, if the null is true, I could have seen this result like 30% of the time. That's not that weird. Then I would say that you either retain or someone will yell at me, it's not retain, it's do not reject. And I say, whatever, because no one talks like that. We retain the null, and I would say that the result is statistically non-significant. Meaning, even though it's not exactly zero, it's close enough to zero that it could have happened just from normal sampling fluctuation. Like this time I got lucky and I pulled a sample that has a slope that's a little bit bigger than zero. It's not that different than zero. So I can't really have a lot of confidence that that slope indicates the predictor variable matters. So inside the boundaries means the result is sufficiently expected. It's non-significant. Retain the null hypothesis. The opposite then, the 11. So the 11.28 from our current example, for instance, way outside the boundaries. Really, really unlikely. It would happen less than 0.0001% of the time, if 0 was the true value, that's sufficiently unexpected by our definition, we would say that we reject the null hypothesis. It's unlikely that our sample came from a population where the true answer is 0, and we would call that slope statistically significant. So that's how we would talk about the result. Given what happened, and more importantly, given the expected inconsistency across samples in what happened as reflected by the standard error. Questions. Does that mean we can never prove that it's false, just that it's not likely and we reject it? Yeah. So where you get in trouble is if you say something like, accept the null hypothesis. We just don't have enough information to reject it. It's sufficiently likely that something could have happened from regular expected sampling fluctuation. We can't reject the null. We can't say that it didn't come from this distribution. Does that help answer the question? Yeah. Okay. I think I have pictures. Pictures always make things better. Yeah, I do. Pictures always help. So this slide is designed to explain why I think one-tailed tests are bullshit voodoo. So let's say that I have this is my standard normal distribution. This is used to provide an estimate for how likely any given result is, where the middle of the distribution is the null hypothesis. So in this case, the middle is 0 because that's what the null is. But if I had a hypothesis say that the slope was 5, right, then the middle would be 5. And the x-axis tells me how many standard deviations away from the null my slope is, in which the standard deviation is the slope's standard error. So a standard error again, how far off on average any one sample slope is expected to be from the population slope. So z is scaled such that 1 is the standard deviation. So we've converted it from units that are specific to x and y into this sort of generic space where 1 is always the standard deviation. So in this case, if I had a one-tailed hypothesis that beta 0 is expected to be greater than 0, that would mean that in terms of divvying up all of these possible slopes, that I would put my money all over here. So I'm testing with this boundary that anything to the right is going to happen 5% of the time, and everything to the left is going to happen 95% of the time. So I have loaded up where unexpected is to only be on the right side. So I'm testing whether or not the slope that I got is bigger than 0. So if I land over here, then yay me, my slope is bigger than 0, significantly bigger than 0. And if I land anywhere over here, the conclusion is my slope is not bigger than 0. Now, where could this go wrong? What if my slope was referring to treatment for a disease? And I really hope that my treatment makes people healthier. If I want my slope to make people healthier, maybe I want a positive slope, right? So if I had a result that was over here, I would say, yay, my treatment worked. It made people better. But if I did a one-tailed test and I ended up, say, over here instead, then I would say, my treatment didn't make people better. But what actually happened is that my treatment made people worse. That's not the same thing. My treatment didn't help is not the same thing as my treatment made people worse. So a one-tailed test would lump together every possible outcome from not better all the way to not worse into significantly worse. All of this would be considered, nope, not significant, doesn't matter. And there are very rarely cases where the other direction is either impossible or otherwise not applicable. If I had a hypothesis that went the other way, then I would load up this 5% over here as my definition of unexpected, and everything that way would be expected territory. So in this case, if I hypothesize a negative slope and I end up over here, I would say, yeah, it wasn't negative, and that'd be the end of the story. I wouldn't say it's positive. So in everything that we're going to do, we're going to allocate the possibility that what I could get could be either positive or negative and be unexpected. That's a two-tailed test. Okay, how are we doing? Oh, solid thumbs up on that one. Yeah. Can I end with a story? It's a true story. So this distribution that I just showed you a couple minutes ago, yeah, it turns out it doesn't work. That's the part that they don't tell you. Yeah, this doesn't hold. This only holds if you have giant sample sizes. And do you know who figured this out? There was somebody who worked at the Guinness beer factory in the late 1800s. I can't remember his name right now. I should know this. Well, Gossett, something Gossett. And he was tasked with judging batches of whatever the hell people make beer out of, hops or yeast or, stuff, right? I don't make beer. I don't know these things. If this was a story about wine, I would be much more informed, but it's about beer. So he was judging samples of these things to make sure that they were meeting the specifications needed to make good beer. And he was flagging certain batches of them as being, nope, this is too far off. Like my hoppiness is supposed to be 6 and this batch was 8 and that's too far away. And so we're not going to use it. But lo and behold, the batches that he rejected because they were too far away from what they were supposed to be, those batches went to get further testing with more in-depth methods. And it turned out that a lot of them were actually fine. And so he was all, what the hell? Like, why is this not working? And he did what anyone in that situation would do. He decided to go to graduate school and get a degree in statistics. And he, by hand, figured out what is now known as students' t-distribution. Because when he figured this out, he wanted to publish his results, as grad students want to do. And the people at Guinness were like, yeah, no, we don't let people publish because we don't want company secrets getting out. And he's like, but this is about a t-distribution. This isn't a Guinness thing. And they're like, it's okay, but you can publish under a pseudonym. And so he published under a pseudonym of student. And that was one of this guy's main contributions. So he figured out by hand, not only that this doesn't work in small samples, but what you should do instead. And so everything that we're going to do is going to be using a differently shaped thing that's very similar but different as a function of sample size known as a t-distribution. What he figured out is that where unexpected starts has to be different as a function of sample size. So for instance, if you only have a sample of 3 people, then in order to still hit that same, like 5% of the time or less, you'd see something this discrepant, you got to move way out here to where unexpected starts. There's more probability in the tails, the fewer people you have in your sample. And so this distribution is flatter, flatter, flatter. As you get more people, it condenses to look like the z. So at sample size of infinity, t and z are the same. But until you hit infinity, they're not the same. So everything that we're going to do this semester is going to refer to t as how we define unexpected, because it works more universally in smaller samples, which is what we most of the time have in social science. So beer to the rescue. That's the moral of the story. Beer makes everything better. Here's a picture that shows the difference. So where do the boundaries lie on these 2 different curves as a function of where unexpected starts, and as a function of how many people, and how many fixed effects you have. So sample size minus intercept and slope right now. The dashed lines are the critical values for Z because the standard normal doesn't care how many people you have, whereas T does. So as you get more people, the difference between T and Z collapses until eventually it doesn't matter, but it still matters quite a ways. So I was always taught that 30 is sort of the magical cutoff where you have enough that it doesn't matter, but that's not actually true. So the good news is that which version of T you need is not something you guys have to figure out. The software knows. It knows which of these is the right set of critical values to define where 5% starts, and it automatically uses that to give you the probability that your result would happen if the null were true. That's our p-value. So there's going to be no tables in the back of the book. The software is going to tell you exactly what is the probability of getting a result as that you got if the null hypothesis were true. How far out are you? And if you're within 95%, then you would say, yeah, not far enough. That's within expected territory, not significant. And if you're outside of that, yeah, that's pretty far away. We'll call that reject the null. We'll call that significant, noteworthy, publishable. Okay. Questions as we wrap up for today? Okay, fair enough. Well, then office hours start now if anyone wants to hang out and talk to me. Otherwise, have a great weekend. Let me know if you need help with your homework, and I'll see you next week in person, unless you hear otherwise. Bye, folks.